Hi, so welcome back to Econometrics B. Today it's about multinomial responses, which is the natural extension of a binary response, namely whether there's just more than two outcomes. So that's for today. We're going to look at Woolrich chapter 16. Woolrich it's rather brief on the topic, so I draw on a little bit on Ken Train's textbook and specifically on the chapter about logit. I mean, you'll be able to find it on his website, or purchase a book if you really want to have a good book. So that's actually a great recommendation. It's one of the best texts on discrete choices in the world. It's like cited, tens of thousands of times, probably 20,000 times. So it's a very popular book. Anyway, so when a response variable has a finite number of outcomes, we say it's a discrete response, in contrast to a binary response. So, and this can be classified into various different categories, and here's some of them, like unordered responses. That's what we're going to look at, like the natural extension of the binary choice. And here's an example. Could be like choice of transportation. So it could be like, should I take the car? Should I take the bike? Should I take the bus? Should I take the rollerblades? Like different. Should I take the metro? There's like many different types of transportation you could you could utilize if you want to get from from home to work or wherever you want to go. Okay. So that's like a clear that's an example of an unordered response. Like, for example, it's not clear that taking the bus is better than the metro. I mean, factoring into account that you have to think about where are you relative to the bus, where are you, what are the prices, there's different attributes to each of these alternatives that may explain why you want to take, say, the bus rather than the metro, or the car rather than the rollerblades, and so on and so forth. Okay, so it's not like there's a natural ex-ante ordering that car is just always better than bus. Some people actually, for environmental reasons, for example, like to take public transport. So then there is rank responses, and see here you get a little bit more variation about the underlying utility or preferences for the agents, because here you would get the information about how the respondent ranks these alternatives relative to their attractiveness. So in the transportation mode example, it would be, you get the information that the agent prefer car to bus to rollerblades, or it could be some other respondent, actual like rollerblades more, so say prefer rollerblades to car to bus. Okay, so so here you get more information. Not only you don't only observe what is the preferred choice, but also the second best and the third best, and so on. And another example that would be like, for example, when you had to sign up for a study, right? You applied a different via this coordinated sign up. You would say, okay, I want to go to economics first. I want to, or say, computer science and economics first, obviously, and then maybe I want to be a doctor or a lawyer, or you list all these alternatives relative to your preferences, and that is basically the information that you get if you look at the data from the coordinated sign up, or coordinated tilmelding in Danish. Okay, so that would be another type of data, because you can reveal from looking at those responses that actually what was the preferred, what was the second option, what was the third option. Okay, so a ranked response, that's different, and we're not going to look at that, but you can estimate models of ranked response by something called the exploded logit, whereas you would be like using a conditional logit or multinomial logit for an unordered response. Then there is something called an ordered response. Here you would say essentially it would be clear ex ante what the best outcome is. Like, for example, if you were looking at the evaluation of the lecture, it could be awful, acceptable, awesome, and it's clear that awesome is just better than acceptable, that is better than awful. Okay, so in those cases, what you usually do is you formulate the model in terms of one single linear index, or some index function, just like we had for binary response, something like x beta. You would estimate the thresholds that kind of divide that latent variable into the to the different outcomes. So, for example, if that latent variable is less than alpha, well, you're going to take awful. If it's between alpha and beta, well, then you're going to be acceptable. If it's larger than beta, well, then it's awesome. And you will estimate alpha and beta as parameters. Okay, that's something called the that can be estimated with something called the audit logic. That's kind of the second part of the chapter in Woolrich, chapter 15. And then there's something called count data, and this happens in numerous cases. We're not going to look at that. It's also a discrete outcome. For example, the number of hits on a homepage, or the number of people that show up at a restaurant, or the number of people who are getting COVID infected. Okay, so here. Or the number of goals scored in the football match. Okay, so it's like the number of something. Okay, we usually model this by for example, Poisson regression models, or if there's like a specific or more, probability mass at exactly at zero that can't be explained by this relative restrictive model, well, then we're going to use something called the zero inflated hurdle models, and there's various extensions for count data. Anyway, that's not something we cover in this course, but there's a nice chapter in that in Woolrich. So we're going to focus exclusively on unordered responses throughout today. Okay, so that's really the topic: unordered multinomial responses. And so here's some more examples. I mean, this could be like levels of education. It could be, should I take a master's degree, a bachelor, high school, or no education. It could be various fields of education, like we kind of alluded to before. You could also model that. I mean, not when you're looking at the application, like at the coordinated sign up, but if you think of modeling what people actually choose, right? Well, then it would be like, what should it be, like a dentist, or a garbage collector, whatever, different types of education, different fields of study. That will also be like unordered alternatives, right? At least if you don't get the information from the agent who is choosing what, or what is preferred to what, like at some ranking of the alternatives. It could be job types, construction, service, clerk, research, garbage collection, various different job types or occupations, or self-employment, wage employment, unemployment, whatnot. It could be different commodities that come in like kind of lumpy, like different commodities, like cars or houses, or regions of residence, or if you're in the car choice example, would be like, should it be like a Ford, a Fiat, a Skoda, a Mercedes, a BMW, Volvo, and so on and so forth, right? Should be like an electric car or non-electric car? Should it be a new car, an old car, or different ages of different cars? You can formulate the choice set in many different ways that involve some kind of discrete choice, or you can combine those, and then you get like a bigger discrete choice set, like should be like a new or old Ford and a new and old Fiat, and so on and so forth. Okay, so that would be, and so that's, you can already see there's like so many different applications of discrete choice models, and this appearance in microeconometrics over and over again. So and so we will usually have, so in the unordered case, we will have data on what the actual choice is. So for example, in the levels of education choice, it could be that you observe that someone has chosen that their highest level of education would be like a master's degree, and then it would kind of, by the principle of review preference, you would know that the utility of that choice would be better than any other alternatives, taking into account all the the explanatory variables and stuff we condition on. And what would that be? That would be like characteristics of the alternatives, and then the characteristics of the decision maker. Different people make different choices. That's why we are essentially trying to control for different decision makers. So this could be like the age, a personal background, parental education, and the distance to university, things like that, things that varies with the individual. Then there will be like characteristics of the alternatives. So this could be like, what is your personal interest? I mean, you're going to study something that's going to interest you, and so there could be cost of different studies that varies across the different educations. maybe not so much in Denmark because we all get student benefits and free education, but like in America, there's certainly a lot of differences in tuition fees between different universities, between different fields of study, and so on and so forth. There will be differences in study time, the differences in expected wage, differences in expected employment rate, things like this. Some of these things you would have to estimate, some of these you would have direct data on, but the key point is that this varies across the different alternatives. Okay, so you want to basically write up a model where the choices you observe are in some sense optimal choices, taking into account the different options that the agent has, and also taking into account who's making the decision. So that's xj and then xi, and then the choice is in some sense rational and revealed by the principal and review preference to be whatever you observe in the data that's consistent with utility maximization. So that would be the type of data that we have. And then in order to say anything about utility, well, we need to have a utility model, and that's actually that's what we do when we try to model the discrete choices and rationalize what people do in different things. Is we formulate utility functions that are functions of whatever the individual has of different options, and the choices, how the attributes of the choices vary, and also how those individuals, how those decision makers vary. Okay, so we want to, in order to estimate the model, actually estimate the parameters of that utility function. Okay, so we want to formulate a utility function that's like a parametric functional form. Oftentimes it's just linear, but it doesn't have to be. And then estimate the utility parameters that, for example, reflect what is the marginal willingness to pay of various things, or what is the marginal utility of money, things like that. That will enter into utility function. Okay, and those parameters that you put in here should be chosen such that they, rational on average most of the agents in that we observe. Okay, so that's kind of the idea. Okay, so now just get a little bit of notation straight here. First, we want to extend binary choice models to multiple alternatives. We need more than just 0 and 1. So we're interested in modeling the conditional choice probabilities. Sometimes we just call those CCPs for the conditional choice probabilities for a finite number of alternatives. So it's important that it's finite. Okay, so they're not a continuum of them, otherwise it's not a discrete choice. And we label them from 0 all the way up to capital J. Okay. Then we're interested in that conditional choice probability. Well, that depends on some explanatory variables that could be like varying across alternatives or varying across the different decision makers, or both. And that is the probability that y is equal to 1 conditional on those observed variables. That's why we call them like the conditional choice probabilities. So these are the conditional choice probabilities, and we would like to formulate models so that these are between 0 and 1. Okay, and then because these probabilities are essentially mutually exclusive, so they will have to like sum up to 1. Okay, and they're all between 0 and 1. So we know that once we sum all them together, they have to be 1, and we can then derive the last say one alternative, say the benchmark alternative 0, as basically 1 minus the rest, or the sum of the rest of the alternatives. Okay, so here I'm summing essentially from 1 up to capital J. Okay, so because it's only with this additional alternative 0 that they sum to J. So you can calculate the last one once you got. It's like the end of the binary example we had previously. The probability for y equal to 1. Well, then your probability of y equal to 0. That's just 1 minus that probability. Okay, and now it's just 1 minus all the other probabilities. So these are simple things, but we need to like get these things straight, and it's kind of good to get a little bit of notation straight. Now, I'm going to move on now to something called the random utility model, and that's like the underlying structural model that motivates how do we actually get those conditional choice probabilities, like we did in the binary case. We wanted to like write up a model for those response probabilities. And we're gonna do the same now. Now it's just a response probability over more outcomes. Okay, not only 2 outcomes but several outcomes. Okay, so that's the idea. And the idea here, the overall idea is really utility maximization. Okay, so what we do is that we basically we formulate a utility function that describes a utility for all the different decision makers I over all the different alternatives that they face. Okay, so Ford, Fiat, Mazda, Mercedes, Tesla, BMW. It's a car choice. Then different utilities or different choices are associated with different utilities. Those preferences are different across the different individuals. That's why it also varies with I. Okay. Now, of course, we're gonna try to model this as a function of explanatory variables, and I've kind of not I've kind of suppressed that part of the notation not to make it too cluttered. Okay, our model here is we usually assume that there's like a utility is separable between what we call like either the representative utility or the observed component of the utility W or Vij. So that's like a observed component. That's like a deterministic part. Okay, so it depends on things we as a econometrician can observe. But then there's a random part, an error term, if you will, stochastic part, which is observed to the decision maker, but not by the econometrician. So it's observed to the decision maker in the sense that the decision maker is maximizing utility based on the sum of both the deterministic and the stochastic part. So how could they maximize utility if they did not observe it? Well, then there might be take expectation over it, and then there'll be uncertainty, but we don't have that. Okay. So here this is the this is observed component. Then you got like an error term, and we really need that error term, right? Because without it, you have a deterministic outcome, right? And then all the probabilities would be either 0 or 1. And you want to try to estimate a likelihood function that depends on zeros and 1, and any data set, you're going to reject that model. Okay, that's why we have error terms. Okay, and this is a role that is playing. So basically, from this formulation, we can derive probabilities that y is equal to 0, y is equal to 1, and all the way up to capital J. Okay, so that's why we have the error term. Okay, by the way, y, that's what we observed. That's the alternative chosen, 0 up to capital J. We model usually individuals, and they're indexed from 0 all the way up to n, and alternatives again 0 up to j. So how do we specify that utility function? Well, essentially, there is many ways you can do this, right? That depends on your problem. You would have to, ideally, you would have to adapt the functional form of this to your application to tailor make your model to what fits the situation. Having said that, there is some things that are very popular and used frequently. That would be, for example, the conditional logic model. Okay, in the conditional logic model, we have Vij being this linear index Xij beta. Okay, so you have variables that now the key thing here with the conditional logic is it varies across alternatives. Okay, so there's an index J here. Okay, this is important. Importance is in the detail here. So now you got information about different, say it's a consumer good that people making choices over. So these goods have different goods have different attributes, different prices. So in terms of cost, could be different weight, different fuel efficiency, and so on and so forth. And then there's the multinomial logit. A multinomial logit, there is we usually just have that it is the explanatory variables that is varying across the explanatory variables varies only across the cross-sectional units. So this could be variables like income, in case you're in a car choice setting, it shouldn't matter for the different choices. Not like if I buy a BMW, suddenly I increase my income, at least we kind of not look at that situation. I could be your age or your education, things like this, things that doesn't vary with choice. Okay, if you have that, we have to have a beta J depend on alternatives. Otherwise, you would not have any alternative specific variation. And in some sense, all goods are equally good, right? It doesn't matter for the optimal choice. And this is something that's going to be a key to identification, as we'll elaborate a little bit more on later. Okay, And then, of course, there's a combination of the two. It's not like, either you have things that only vary over the individuals or only over the choices, or both. And so that's time in a little bit confusing way called the mixed logit. And there's several people that calls it the mixed logit. Woolrich calls it the mixed logit. Cameron Trivedi, another textbook, calls it mixed logit, because it's kind of the mix of the multinomial and the conditional logit. But Kenneth Train and a whole discrete choice literature calls the mixed logit basically what other people called a random coefficients logit, or a logit where you have error components that varies in a random way, like you have like a random effect. That if then there is the epsilon here plus some other error term, and this epsilon is I at extreme value, and then you have that error term being something else. So that's actually a mixture of two components you got. That is called a mixed logit. And there's a whole chapter about mixed logit and actually lots of the book, a lot of the book of Ken Train's book is about mixed logit. So just to make that distinction clear here, that's a little bit potentially a little bit confusing. Now, I haven't talked much about the error term, and like for the probit, we would have this would be normally distributed. For the logit, this is set to be IID extreme value distributed, and then additive in utility in this particular way. Okay, so you haven't probably heard about the IID extreme value distribution, but let's talk about it. Okay, I'll get back to it. The IID extreme value distribution has the property, if you take the differences between two alternatives, it becomes logistic. At least in the binary case, it collapses to the binary logit model. So anyway, we'll look at it. We'll look at it in just a minute. I just want to say a few more words about utility. Like here down here, we kind of alluded to the utility, the deterministic part of utility would be like a linear function, and it doesn't mean it by no means it has to be like that. Okay, it could be, for example, an indirect utility function from a static optimization problem that involves other choices. So are the continuous choices, for example. So suppose that in the car example, that the choice could be, say, how many kilometers do I want to drive? Okay, so what's my demand for kilometers with this car? What is my demand for using it? Okay, in this case, there'll be this continuous choice. But now, of course, that depends on what car I have. If I have a very crappy car that never starts, I'm not going to drive it. Or if I, for example, have a very fuel efficient car, it doesn't matter so much for my economy, and so on and so forth. These choices depends really on what is the car that you have. And so, but then what you could do is you could like write up the utility function for all the different car choices, conditional on that choice, and then find the optimal amount of driving for each of those. That's called that like C star, the optimal amount of C. You put that into each of those utility functions, and then you have something that depends only on the different choices. Okay, the different discrete choices. You kind of once where it's an indirect utility where you have obtained the highest maximal utility by maximizing with respect to the driving choice or whatever that choice is. Okay, so that's another example. So often we combine different models, like some parts are discrete, sometimes are continuous, and so it doesn't always result in a linear index, right? Nevertheless, this framework allows for that. Then there is a choice-specific value function, could be in a dynamic discrete choice problem. This is, now we're really going beyond the curriculum. But what I'm trying to say here is you can formulate these alternative specific values that depends on the different choices in many different ways. And here's one for a dynamic choice problem where you would choose in every period what car for example, should I own? Should I buy it? Should I trade it for another one? And so on. That affects current utility, but it also affects the future expected utility, because if I don't have a car today, if I sell my car, I'm not going to have the car tomorrow unless I buy another one. And then you need to calculate the kind of the continuation value of whatever choice you made. And this is in itself a function of what the values of different of being in different states and having different types of cars that is. Anyway, this is way too much. My main point about this is just it doesn't have to be a linear index. Okay, so we can really form very flexible economic models that involves discrete choices. Okay, so back to conditional logic and multinomial logic. Just to wrap up a little bit, you know, to get us back into track. The conditional logic, that's a model where we have like k characteristics of alternative j. So there'll be like k explanatory variables, and then there'll be like k coefficients for each of those, for example. And then that will have the interpretation would be what is the marginal utility of that attribute. So because if you think about it, you know, this is utility, you differentiate this guy, our utility function here, you differentiate that with respect to x, well, then you get beta, right? So that's, since that inside the utility function, it's like the marginal utility of that attribute, okay? So for example, like suppose we're talking about the size of the car being one, then, you know, beta to the size of a particular car, that'll be like what is the marginal utility of a size of a car that you estimate. If you're assuming that you have like a linear index, well, you assume those marginal utilities are constant and does not depreciate as, or does not diminish as cars get bigger and bigger. Okay, so maybe you want to, you know, specify, if you think size has a decreasing effect, you may want to have like a size squared in the equation too. But, you know, this is a matter of empirics, if what fits the data well and what is also fits the theory well. Okay? So yeah, I guess here I took an example of educational choice, but, you know, that's just one example. Here we already talked about that. Key thing is you need to make a normalization, and you really need to make sure you cannot have, this means you cannot have choice specific intercepts, and you need to fix a scale. So you can have like a scale factor on the epsilon. That was just exactly the same as in the binary case. We can look at those identification and normalization identification issues that are solved by normalization a little bit later. Okay, for the multinomial logic model, well, here we only have one parameter for each of the different attributes of the good, but down here we have more parameters. Okay, so we actually, because this is the situation where we have characteristics only of the individual, and since there's no variation across the different individuals, well, we need in order to make rationalized by people choosing different things, like you need variation across the different alternatives. The only way you can get that is by putting them into beta. Okay, so beta varies across alternatives. This means that if you're estimating like a multinomial logic model with like 100 different alternatives, well, then you're going to get 100 parameters potentially, right, for each of these explanatory variables. At least if you, unless you restrict some of them to be 0 or something else. Okay, so this is like very parameter intensive if you have many explanatory variables and many alternatives. And here we need to do the kind of essentially the same type of normalization that fixes the level of utility. One thing that's often done is by normalizing utility of alternative 0 to 0. Which means in our case that beta not for that alternative of beta 0, all the betas would be set equal to 0. So that means essentially that the interpretation of those beta coefficients after that normalization would be the utility dependence on these explanatory variables for alternative j. So here j, the alternative j refer to the coefficient relative to some baseline alternative that we normalize to 0. Okay, so that's important to keep in mind. Then you get different coefficients depending on how you normalize the model. But it doesn't really have any effect on the overall probabilities, which is why we made that normalization in the first case. Okay, so it's just a matter of how you interpret the coefficients, and you need to kind of compare all the coefficients to other coefficients of other alternatives in order to actually understand what the effect is. Well, we'll look at that. Let's just take some time to see if we can derive the choice probabilities. So far, we pretty much just talked about utility, the utility maximization framework, how those utility functions may be, you know, linear or nonlinear, and, you know, the additivity of the utility function. let's look at how do we get that response probability, because looking ahead, that's what we need for estimating the model, for confronting the data and writing up the likelihood, and for making making predictions. Okay, so so that was kind of our starting point. So let's try to see if we can solve that. So what we do is we can derive in a completely analogous way to the binary case. We write up the probability that yi is equal to j as basically uij being greater than uik for any other alternatives. In other words, what is this saying? It's the same that it's saying up here, that the agent is maximizing utility, because it's equal to the argument that maximizes the utility, that's equal to one of those j's. Okay, so if j was the was the highest alternative, well, then it must have been that the utility of that alternative was bigger than for any other alternative. Okay, so that's the probability for y equal to j. So this is the same. Okay, now we can just substitute this guy here in here for the two different alternatives. That's what we have done here. Move a little bit around, and then you get some stochastic variables that have to be smaller than something that's deterministic. Okay, now if you know the distribution of this guy here, this is like suddenly a joint distribution of capital J different random variables. Well, if you know that, right, then you can calculate what that probability is. And so you just put those utility differences into that CDF, and then you got essentially your response probability. Now it's slightly more complicated. It's actually much more complicated now to express that utility here in closed form. For example, it doesn't exist in closed form for the probit model. So, but one of the things that makes the logit model very attractive is that we get a closed form for this expression. Okay, the bottom line is it depends on the distribution assumptions of the error term in this random utility model, what those probabilities are. And then the question is, how do we choose that epsilon distribution, and what would be the implied distribution of those differences? Okay, so this is now we talk about the type 1 extreme value distribution, sometimes distribution, sometimes also called the Gumball distribution. It's a or standard Gumball distribution. The Gumball distribution has shape parameters, and so this is the standard one, just like we have the standard normal distribution where the standard deviation is 1 and mean is 0. And so the cumulative density and probability density functions are the following. And because see, these are nice functional forms, right? Because they don't only depend on simple exponential functions, and they're easy to differentiate, they're easy to calculate. It's like we don't need to do any integration or anything to obtain this CDF. And it's bounded between naturally between 0 and 1. So you get epsilon go to minus infinity, or then this is going to be infinitely large. You got infinity here, so you got negative infinity and exponential of negative infinity. That's essentially 0, right? And then the other way around is going to be 1. Okay, so you can kind of try it out. And then here's the densities, and that's just the derivative of this guy. And you can take derivative of exponential functions. And so we have to just remember to multiply with use chain rule to get the inner derivative, and so that's what you get here. Okay, so the Gumball distribution, what is the nature and sources of this guy? It's what it arises as. It arises as a limiting distribution of the maximum. Okay, it's a limited distribution of the maximum of n random variables drawn from the same distribution. Okay, popular examples are earthquakes. Like we model this use this for predicting extreme events. Right? So and then if the distribution of all these extreme events, well, that's going to be extreme value type 1 distributed. Okay. So why are we using this particular distribution for discrete choices? Okay, we like not as economists think that consumers are extreme, right? but this thing that it's a limiting distribution of the maximum, well, you know, this remember that it's not really the differences doesn't in utility doesn't really matter. So once you take differences in those ID extreme value terms, they actually not look that extreme. Okay, so here's here's a distribution. Okay, so here's a distribution, and it's skewed to the right. And then the question is that a problem? Normally we would like, you know, have, you know, mean, zero, and a symmetric distribution, just like we have in the normal distribution, right? It's an error term. But then remember that if these extreme value distribution here, I wrote GEV for generalized extreme value to allow this generalization that allows for some correlation. But if these are both extreme value distributed and independent from each other, then the difference is logistic. And really, you know, that already there, you can see the whole thing boils down to the binary logit model, because if this is logistic and you got two outcomes, well, then these then this is like a logistic distributed variable, and then you got already just put that into your original logit formula, you got your binary logit model. Another property here that is very convenient is that the generalized extreme value distribution is max stable, so that if you take the maximum of n different GEV distributed variables with parameters, with same parameters, then they are also generalized extreme value distributed with the shape parameter unchanged. And we also get some nice closed form for the expectation of the expectation of the max of many different ID extreme value terms that has a nice closed form. So these are very practical things that makes econometrics easy, because the alternative is this. Okay, now if we just forget a little bit about logit for a second, or those ID extreme value, basically the response probability looks like this. Okay, so again, you got utility maximization. We put in our additive model for utility here. So you got the error terms that was ID extreme value before. We can move it a little bit around to get what we have here, and then that probability. Well, that is really a probability. Well, that's an expectation over the indicator function that whatever is the event we are looking at is true. Okay, so in this case, it would be that those epsilon differences would have to be smaller than the value function differences for all the different when difference occurs, all the other non-chosen alternatives m. Okay, so j here is the chosen alternative, m is the other alternative. Okay, so and then the question arises: how do you calculate that integral? And you know how to do it, right? We just have numerical methods. We know how to calculate multivariate integrals. You know, you could simulate it with Monte Carlo, for example. And many people do that. And actually, this is one of the cases where you can really power up your computer and your numerical analysis skill and do more flexible models. Because what I'm going to show you now is how you get a closed form, and it's gonna be clear to you that it implies some unfortunate substitution patterns that are implied by the assumptions that we are making. Okay, and then instead of motivating your model by what you can compute analytically, we can motivate the specification of a model based on how we think it should look, how it captures the situation we're modeling, and how it fits the data, right? So that's very popular to simulate those integrals, okay? But we're not going to do that. We're going to first look at the logit model and see how far we get with that. And that's a beautiful model, beautiful model. Okay, so in general case, we really need to, evaluate this multidimensional integral over unobserved portional utility, those epsilons here. And then we can kind of reduce it by one dimension because we difference against one alternative, but still it's a j-dimensional integral. If you have time series variation too, and you want to model the dependence and a completely unrestricted dependence over time, well, then each of these epsilons, they're t vectors, and then you have like a t by j-dimensional integral, and you can see this this potentially grows very big, and then with large choice sets and long time periods, this could be computational very demanding. You have to think about actually using some of the structure to calculate things that you may think actually could potentially be done analytically, and then the other things that you think, oh, I really need to add that to the computer. So here's how we derive the response probability in the logit case. This is the simple closed form choice probabilities that you get, and they look like this. This is the result. Okay, so now if you fall asleep, the only thing you need to remember is this formula here. Okay, this is the logit formula for the conditional logit. Okay, and also for the multinomial logit, you just that does just depend on how we specify the deterministic portion of utility. Okay, so here we are. We got your utility maximization, and then you see here you got utility of alternative J bigger than utility for any other alternative M different from J. Then we need a bracket here. Why don't I just put that in right away, so I can I don't forget. Okay, so okay, so now we could do is we can condition on epsilon J, like assume we know it, and then derive the probability conditional on knowing that epsilon. Okay, and then we move it to the other side. Now we get a univariate, essentially a univariate probability, and well, we got one for each of all the other alternatives than J. But since all these epsilons here are independent across all the different alternatives, what do you do? Well, you can just calculate the product of all those probabilities. That's what you do with independent events. Multiply them together for all the different alternatives other than J. Okay, that's why we have this product sign here. And then essentially, what is that we have here? Well, that's a CDF of epsilon IM evaluated at what we have here. Well, this is our CDF, right? Remember the functional form for the CDF was what was that? That was this guy, like minus exponential minus epsilon. So that's essentially what we have here: exponential minus exponential, and then this should have been to the power of e. To the minus this guy. Okay, so what we have inside. So essentially, it's just a product of all the different probabilities. And so, in other words, in order to get this probability not conditional on that epsilon, because we don't really observe that, right? To get that probability, well, we just need to solve a one-dimensional integral instead of like a j-dimensional integral. And so how do you do that? Well, you take this function that you want to integrate over, multiply by the density of what you're integrating over. Well, that's the density of the extreme value term, and then you'd integrate over the support of that. Okay, so in our case, it would be like minus infinity to plus infinity. And then we can show that we get a closed form for this unidimensional integral. And that's on the next slide. And I think it would be too much to go through the derivations, but now at least you have it in the notebook. Basically, it's, well, there's not that magic. Most of what we're doing here is, in principle, high school math. Well, what we're doing, this is just turning the product, putting that inside the exponential. That makes it a sum. And then what we're doing here to get rid of the m different from j is to realize here that for m equal to j, well, you have a term where the value function difference is 0. So that's why we suddenly do not have that m different from j here in that product. So we could just for free add it. Then we move a little bit around and make a substitution here, or make this substitution here, so we end up with this integral here. Okay, and then I think and then we are trying to solve that integral. I'm just continuing down here, and then that turns out to be the logit formula. Okay, well, you didn't follow. Well, now at least you know where it is. Okay, and you can see that we could solve it analytically, which is kind of the main point. Okay, so having specified the utilities, well, we are ready to talk about how you estimate this model. Okay, so to estimate model, we need some data. Okay, and just we assume that we have a sample size of n. Each of the units I are randomly sampled. So this pair yi xij is just a random draw from the population, and then xij, just think of it as, it could either have things that varies only over the individuals, or both over the individuals, or and uh, and the alternatives. Okay, so this is the type of, these are the two variables that we have observed, and we have random sampling over the population. If we have panel data, well, then we may want to think that they are randomly sampled over I, but not over T, and so, but this doesn't really change the formulation here in terms of unit I being randomly sampled. Then yi is really just a T vector, and then xij is, well, that's a T by K matrix with the rows being equal to all the different observations. I mean, this depends on how you organize the data, what the size of these matrices are. The point is, it's just T times as many observations, and you draw them kind of in chunks. Okay, so then you need to, if you want to do maximum likelihood, write up like actually say something about how that is how the time dependence is over the time periods. If you just pull the whole thing, well, then we have to remind ourselves this is partial maximum likelihood, like we talked about the other day. It's not different here. So if you do like a pooled conditional logic for your panel data, you need to adjust the variance covariance matrix and use the robust ones and cluster at the individual level. So many of these things that we already talked about just generalizes to also estimating with maximum likelihood. Then a few words about the types of data, where you could have like reveal preference data, where you observe what people actually do. Okay, so that's what we usually see in the registers. In the register data, we see what are all the different costs that people buys at different points in time, and then sometimes it can be hard to actually get the appropriate variation in the choice dimension. Okay, you would have to kind of impute what would happen in the other choice situations. Okay, like but often we can do that. Like, for example, you say, okay, here's a choice that you can choose between car number 1 up to J, and then I observe that the prices are this and that much. I observe that the fuel efficiency are this and that much for all these different types of cars, and then I can just put it on. But it's not like you can ask, what if the price was this, and what if the price was that? That you can only do in stated preference data. Okay, so what people often do this in marketing, you present people for a menu of different choices where they do different choice situations, and so they ask the same individual, are you going to buy Coke or Pepsi, depending on, if this is on sale or this is on sale, you're going to take your favorite brand, and, then you change the prices and figure out how people make their choices. Okay, these are like stated preference data. Now, the benefit of stated preference data is that it's easier to get like variation or counterfactual variation in the data that sometimes you don't really observe that in the registers, in the reveal preference data. For example, because people never choose a particular good. Okay, so of course the downside is, well, do we really trust what people answer in hypothetical choice situations? Maybe less than what they actually do when they have their own money on the counter. Okay, so that's like pros and cons. So you have to be aware of that when you think about actually working with data. Okay, so here's how we estimate the likelihood function. We estimate these models with, we often estimate them with maximum likelihood. It doesn't have to be maximum likelihood. There's also like, method of simulated moments, or there's something called the method of simulated scores. You can do like, there's many ways you can do it. But since we have specified the entire distribution of the random variables, y that takes values 0 up to capital J, why don't we just try out and do maximum likelihood? And actually, once you have specified the utilities and derived the choice probabilities, the likelihood is rather simple. Okay, so here just a little bit of notation. D here, that's an indicator, a dummy for choosing alternative J. They all sum to 1. Then you have the probabilities here. The PIJs, just yeah, I'm repeating myself. We already defined that in some sense. And then you get the individual log likelihood, which would essentially just be summing over all the different alternatives. Okay, like and then pick out the probability for the chosen alternative. Okay, that's what it's saying. I mean, you don't really have to. I mean, all these where it's 0, it's going to be 1, right? So it's really easier just to take, pre-compute a vector of choice probabilities for all the alternatives, and then pick out the element that corresponds to the chosen alternative. That's what the likelihood is. And then that's the likelihood contribution for individual I, and then the log of the likelihood. Well, you just take the log, and then you get this expression. So that's a relatively simple likelihood, and it's the natural extension of what we had before. There was also like a product of two, y is equal to 1. It was probably y equal to 1, and otherwise it's 1 minus y times the probability that y was not equal to 1. Okay, or that probability equal to 0. So you remember that from binary choices. It's just a natural extension of that. Okay. So the question is, how do we specify this guy here? Okay, and we already kind of alluded to, let's work with the logit, and then we get these different expressions for that probability, depending on whether you get the conditional logit. Then you have, it's the one where you have a variation across the alternatives. So you have xi j beta inside the logit formula. Otherwise, you have xi beta j. Only have variation across the alternatives through the constants. This could be variables like age and income and education, background, things that varies with the individual only. This is what you have in the multinomial logit. So they really just differ slightly by the type of variables that enter into the utility function, whether they vary across alternatives like here, or they don't, like in the multinomial logit. And then you have the combination here. Okay, I changed a lot of this only just to x can have they can just to mimic that you have two different types of variables. Okay, so it's really not that a big deal. Anyway, so what do we have here? Well, if you just put this logit formulas into our expression for likelihood contribution, well, this is what you get. Okay, so essentially you can rewrite this a little bit, so you get essentially x beta minus the log of the sum of the exponential over all these different alternatives. Okay, and this is for the conditional logit. Okay, and you would have this stuff inside here if you're working with the other logit. Okay, and then this would change a little bit over here. Otherwise, you just put this stuff right in here. Let's see. The key thing is when you take the log, well, it eats the exponential, right? And then you take the log of a fraction, it becomes minus. Okay. One thing. So this is essentially x for the observed alternative that you have here, right? There's only one of the done is that is 1. So you can put that in, and then you maximize the likelihood with respect to beta. I mean, the average overall of the sample, of course. Okay, so that was all about actually, how to, our introduction about logit, how you got the response probabilities, how the multinomial logit and conditional logit are different, slightly different, how you get to from the response probabilities to the likelihood. And so we are actually now ready to estimate a logit model in some sense. But there are some subtleties about identification that's very important in discrete choice models that we need to discuss first, and that's for the next video.